Okay, we're starting a unit on polar curves. You're now an expert on parametric curves, no doubt about it, and because of the last 6 years of your math career, you're also an expert on rectangular equations or your classic equations. All right, so polar curves, you may or may not have experience with these, but if you've ever seen this thing, you've probably referred to it in somehow or another related to Spider-Man, but it's not. This is a polar coordinate grid, and it's going to make a lot of sense as we go through an example. By the end of this video, we should be okay with graphing by hand. We should be okay with doing it on a calculator. Life will be good. We can move on to other things. This is an example of a polar equation. And r is going to stand for the radius, and theta is going to stand for some angle. And again, those two will make sense as soon as we start going through this. So what I'm going to do is I'm going to start you off with a t-chart of that equation that we're working with right there. Okay, so I input a theta value. In this case, I input a theta value of 0. As I do the math, I get out an r value of 2. And I do that with these other 3 points, and you can check my math on that, but I'm pretty sure I'm right. And we could just keep going on, and we would need to pay attention to the domain, and they're just saying, naughty, naughty, don't go past 2 pi. And you can fill in as many theta values as you want, but I bet you're going to want to just stick with the famous spots on the unit circle. And I've taken some liberties to go ahead and turn these values into decimals. You wouldn't be able to do that without a calculator. Okay, well, this plug in a 0, get out a 2 can be written as an ordered pair. You're used to ordered pairs in rectangular coordinates. Now there's something here that will kind of bend your brain, at least it bends my brain. I plugged in a 0, I got out a 2. But for some reason, and I'm not aware of this, I probably should be aware of why, they write the ordered pair for polar equations in the reverse order of what I would think. So be careful when you plug in a theta value and you get out an r value, they're going to write the ordered pair in the reverse of what your instinct might be. So we have the polar equation, we make this little t-chart. Well, why the heck are we doing this? Because, I said we're going to do some graphing, but it doesn't look like we've done any graphing. This is where the Spider-Man graph comes in. So I'm going to go ahead and graph these 3 points, and by graphing these 3 points, you could see why we could graph 27 of those points and make a nice little curve. So I get a theta of 0 and an r of 2. I always think of the theta as the trajectory or the aim, and the r, the radius, the distance we're going to travel. So my brain would say, hey, shoot at a theta value of 0 on the unit circle and go out 2 units. So it's a little difficult to see because this is a lot of detail, but we know if this is the origin of the unit circle, if I go out this way, I'm heading toward the value of 0. That's the direction of 0, or even 2 pi, but we're going to say 0 on the unit circle. And then you have to look really closely. If I go out 1 ring, that's a radius of 1. If I go out 2 rings, that's a radius of 2. So the dot that I just put there is 2, 0. Oops. It's 2, 0. But it's not 2, 0 like rectangular coordinates that you're used to. So we'll see how that shows up here on this next one. Pi over 6 is my theta. R is 3.5. That means I start at the origin. I shoot out at the angle or towards the pi over 6 on the unit circle, and I go out 3.5 units. There's 1 unit, 2 units, 3 units, if I'm counting right. There's 3.5 units. There's my second dot on my graph, and if I had to put that in an ordered pair, it goes r theta, so that's a 3.5 comma pi over 6. Got cut off again, sorry. 3.5 comma pi over 6. Now you definitely know that you're in or you suspect that you're in polar coordinates, whereas 2 comma 0 you could kind of guess either way. All right, next point. Pi over 4 is trajectory. Go out a radius of 4.121. So pi over 4, I don't have it labeled on here, but it would be right up there. So I'm going out at this direction, and I go out 1, 2, 3, 4, and a little bit more. What would be about here? And that is an R of 4.121 and a theta of pi over 4. All right, so we have three of these points now, but you can imagine if we had a bunch of them, we would be able to connect the dots and we'd have a graph that would be swimming around. Who knows how it's going, but you're about to find out how it's going. So that's the basic graphing by hand. And now I want to show this one to you on the calculator. Okay, here I am in the calculator. I understand that there's probably better technology than just shining a camera on the calculator, and the lighting might not be so great, but we're going to get this done. Here we are in the classic y equals rectangular mode. So to go to the polar mode, I click mode, and you're familiar with messing around with parametrics mode. Right there is polar mode. And now if I go to the y equals screen, doesn't look too bad. It's r equals, and we're working with this equation 2 plus 3 sine theta. I've already made sure that my window is appropriate just for the dramatic effect. Watch the graph of the equation that we were just working on. Isn't that beautiful? And people can make very, very beautiful, symmetric and pleasing to the eye graphs with these polar coordinates and these polar graphs. So I want to point out to you things that you have to become good at. In your window, you get to give the calculator the range for theta values that you want to use. So here I went 0 to 2 pi, and look what happens if I just go 0 to pi, and I'm going to go ahead and regraph that. Oh, that's disappointing. I feel incomplete because in this case I had to go to 2 pi to get the full graph, and I don't know of any great way to know how far to go, so you're going to have to be good at trial and error. If I went past 2 pi and graph it, no big deal. You may not even be able to tell, but it'll just start retracing over itself. So it's retracing over itself, but it doesn't matter because it's going to do that thing. I think it would do that thing for 37 years or as long as your batteries last. I'm going to go back to 2 pi here now. And this is the step at which the calculator advances to the next theta piece. So I can't remember what I have here. You can mess around with this. So for example, if I entered, I just wanted to go by half pi steps, that wouldn't be very good. That means the calculator is going to go from 0 to pi over 2 to pi to 3 pi over 2. If I do that graph, it's going to look really clunky. Oh, a little bit like a spaceship or a warhead. If I go ahead and be a little bit more reasonable, like say, hey, I want to go pi divided by 3 steps. It's not much more reasonable, but the graph will look a little bit better. And I think you're getting the point. And I'm going to go to steps. Let's go pi divided by 6. Now it's going to be even better. So it graphs faster, but it's clunkier. I'll bet you that the standard that I'm using is, I don't even remember offhand, but I'm going to say pi divided by 24. Yeah, that looks like it. I bet Alex Chan recommended that to me, and if Alex Chan recommends something, PHSN Math Hall of Fame 2016, you never argue with that. Okay, so we've got that graphing. Let me show you, you can, like you figured, set your X window and your Y window to be appropriate so you can catch the whole graph. The biggest deal here is you might have to be prepared to do some trial and error with the maximum or the end of your range. You can also do things like second trace or calc, and then like you would expect, you can find a derivative, you can find a value. So if I hit theta equals pi divided by 2, I'm using the value option right now. It shows me where we are at pi over 2. My x value is 0, my y value is 5. Okay, if I go back to this second calc, and I'll just try a dy dx or a dr d theta. We'll be talking more about these later. So I'll do a dy dx, and I'll do it at pi divided by 3. And they tell me that my dy dx there is negative 1.11, which should make sense to you because dy dx always stands for the slope of the tangent line, and the slope of the tangent line right there, if you use my pen as an awkward tangent line, is negative. So we'll talk more about that stuff later, and of course you can just do the regular trace. As your turtle goes around the racetrack, you see that you get an update on the x value, the y value, and the theta value. So going back to our graph we were doing by hand, we only did the first 3 points or so, but if we were dedicated and we really did all the rest of that, we'd end up just connecting all these points and getting that beautiful picture. I've already, forgot a little bit about what it looks like, but it would be something like that, and it would just take a lot longer by hand, as you're well aware of. Let me now give you one final warning. There's a very counterintuitive thing that can happen, and sometimes a problem isn't making sense to you, and it's probably because something like this has happened. The r can be negative. Okay, here's what I mean. As you go through these calculations, there's plenty of equations here that will sometimes give you positive and sometimes give you negative values for r, depending upon what theta is. So that means this. These values here have nothing to do with the problem we've been working on. I just made them up to show this point. But I'm going to plot 6 comma 4 pi over 3. Let's see, can I get these both on here? Kinda. Okay, 6 comma 4 pi over 3. I'll do this in a different color. That means I shoot out at the trajectory of 4 pi over 3, which is right here. So I'm shooting out there and I go 6. So I've just graphed 6 comma 4 pi over 3. But now check this out. Negative 6 comma 4 pi over 3. I shoot out at the trajectory of 4 pi over 3. So I'm shooting out this direction. But now that radius is actually a negative length. So instead of shooting out this direction and going positive 6, I shoot out this direction and actually go negative 6. So it's a little bit counterintuitive because the point that I just graphed is negative 6. Well, let's get this in the picture. Negative 6 comma 4 pi over 3. But that very same point, depending on another situation, could be 6 comma pi over 3. Okay, so just be aware that your r can be negative, and it might play a little bit of trick with your brain because it's hard to process that and that being the same as that and that. All right, it was kind of a long introduction, but getting to know polar curves in the very beginning takes a little bit of talking because you probably haven't worked with these things yet. Eventually, very soon, we'll be doing some calculus.